All right, hey everyone, welcome to the first workshop of the advanced track for winter 2022. We're glad to have you all, either for your first workshop or if you're back from the beginner track. Either way, really excited for this quarter. Unfortunately, I'll be online until at least week 5, I guess. But hopefully by week 5, we can be back in person. And so this first workshop is going to be about it's not listed in the calendar as a membership portal. I see. This could be a problem with the, I'll look into this more later, Jeffrey, about the membership portal. But it might be a bug on the membership portal side because, but yeah, I'll look into it. Thanks for letting me know. Anyway, yeah, first talk for our first workshop, we'll be talking about both a review on logistic regression. So back in beginner track, we talked about logistic regression for a couple of weeks. And so we'll be reviewing that. And then based on that, we'll be moving forward into neural networks. And so we'll get into like the first bit of the basics behind neural networks in this track, in this workshop. If you guys want the slides and also the feedback form, the link is right here, tinyurl.com/apetrack1-w22-form. This is our feedback form, and on that form, we'll have the link to the slides. Really appreciate your feedback, so if you can provide that at the end, it'd be great. Right here is a Discord, and so we'll be posting recordings of these workshops on Discord as well as any announcements. And so if you haven't already joined the Discord, please go to the link and join if you can. Really I recommend it. And the attendance code, it doesn't work right now, but usually we have our membership portal working, and that would have basically ACM wide events present on the portal. And so if you go to members.uclaacm.com, you can see that portal, and usually events will be there and you can log in. And then if you go to the event, you can enter the attendance code to get points towards the end of the year raffle. I think this one's not working right now, but I'll try to get it figured out for next week or maybe even later today. All right, so quick couple of things about ACM AI because it's our first workshop. And so our main mission at ACM AI is to have a community of students that are interested in AI at UCLA, but also beyond UCLA. So wherever you go next and wherever you might go in the future, have that same interest in AI and bring it to other people as well. And so in order to do so, we have a couple key values. The first one being technical proficiency and awareness in AI. And so first off, knowing how to use AI as well as like what its general like methods and techniques are, as well as knowing what's currently happening in the AI space. Next is creating a positive impact in society. I'm sure a lot of you guys have probably heard about like ethics problems in AI, as well as like, I don't know, like neural networks gone wrong, like with bias and problems with bias and things like that. And so it's important to us that we focus on creating machine learning programs or machine learning methods that are having a positive impact in society, because at the end of the day, that's like what we want to do. And we don't want to have like malicious programs out there. And so that's our second goal. And third goal is diversity and inclusion. And so usually the ML space, and I guess CS in general, isn't the most inclusive and diverse space, but our goal is to make it accessible to everybody as well as open to everyone. And so no matter how much experience you have or who you are, you're always welcome at ACM AI. And so to do so, we have our 4 initiatives. You're at one of them right now, which is workshops. And so we teach workshops about machine learning and AI in general. We have our projects division. And so if you're taking advanced track right now, which you all are, thanks for coming. But if you're taking it right now, next quarter you can apply for projects, which is basically taking what we're doing here with neural networks and machine learning models and making it into like a more pipeline approach, where you're actually like making a model yourself and applying it to a problem. And so if you're interested in making your own models and also going through that whole process of finding a problem, figuring out what model to use, as well as actually programming and testing that model on for machine learning purposes, projects is a great place to go. And after this quarter, you'll be ready to actually join the projects team. Next, we have our events team, which puts on a couple really awesome machine learning and AI related events over the quarter. And so if you're interested in anything from like coronavirus AI techniques to like a really intro-level AI class for everyone, events, those things like that. And so they put on some really cool events, and hopefully they'll be in person in the future. In outreach, their last division, where we work with the, I guess, greater LA population, mostly high schools, to see if we can teach them about AI and how they can get involved at an earlier age, as well as our awesome ACM AI podcast, which focuses on AI in LA and some of the really big leaders in AI in the community here. All right, and so for this track, we have 3 officers helping out this quarter. Gonna have Angeline start with introductions.
Hi, I'm Angeline. I'm a first-year Lingen CS student.
Hello, my name is Preetham Pangaluru, and I'm a second-year computer science major, and I'm going to be one of your workshop officers this quarter.
All right, and then lastly, I'm Nikhil. I am another workshop officer, and I'm also helping out advanced track this quarter. And I'm a second-year CS major. Yeah, so we're really excited to teach this quarter and answering you guys' questions. So again, if you have any questions along the way, just feel free to ask in chat or out loud, and we'll be happy to answer. All right, so quick talk about ACM AI projects a bit more. And so this is, again, like I talked about before, working on your first, I guess one of your a bigger machine learning or deep learning project. And so last quarter, people on project teams have worked on some really cool models to either identify plant diseases or identify humpback whales. And so these are really cool projects that are also pretty hard and also like quite applicable to real world problems. And so it's a really cool initiative we have. And so I'd recommend doing it after this quarter. The QR code right here is a link to the FAQs for projects. And so if you're interested in or have any questions, check this out. All right, and then so some quick overview on logistics for our workshop this quarter. So in case you weren't a beginner or aren't sure if to take advanced or beginner track, here's a quick distinction between the two. Beginner track is more about classical AI methods, so things like linear and logistic regression, a lot about math concepts and motivations behind these methods, and it has no prior knowledge required. While advanced track is more focused on neural networks and deep learning. And as a result, we expect a bit of knowledge working with data and Python, as well as some basic machine learning knowledge. If you don't have that yet, don't be too worried. Just be ready to like ask a lot of questions and I guess be curious to learn, because we can always help you out. And then so tentative schedule for this quarter. So we have this week right now, week 2, which is the intro to neural nets, feed-forward neural networks, which are the, I guess, most like the first level of neural networks we're going to learn about, and a review of logistic regression. Next week, we'll be looking into more logistic regression, as well as 2 really important, this would be feed-forward, but 2 really important aspects of neural networks, feed-forward and backpropagation. Weeks 4 and 5, we'll be talking about a really popular and oft-used type of neural network called convolutional neural networks. It's a pretty big topic, so we'll be using 2 weeks for this. And week 6, we'll be talking about recurrent neural networks and I guess like a expansion on them called LSTMs. We'll get into more. Week 7, we'll be going to PyTorch, and PyTorch is a really cool library for deep learning programming. And so if you want to program a neural network, PyTorch is one of the most commonly used libraries for that. So we'll be introducing you to that, as well as helping you get up to speed on how to use it in more detail. And then weeks 8 and 9 will be a guided project based on all the things you've learned in these first couple of weeks. And so a couple of things with this. So we meet on Mondays. And so as I learned like yesterday, actually, we actually have a couple of holidays on Mondays this quarter. And so that leaves us actually next week is actually MLK Day. And so that happens to fall on Monday. And so I wanted to get your guys' all feedback on how we should proceed with these holidays. So I'm pretty sure that week 3 and week 8 are both holidays for our workshops, but we still want to be able to provide the content to you guys in some form. And so I have like 2 options I've been thinking about mostly, being either, so we have 2, I'll launch a poll right now and I'll explain the options in a second. But basically, what I was thinking is either have it be there as normal. If you guys are willing to show up and actually take it during a holiday, we could do that, of course. The other option is that me and the other officers could record it ahead of time and send you that instead, so you can watch it on your own time. And if you have any other ideas, you can write that in chat and we can talk about that and consider that too. So yeah, please take a second to fill out or respond to that poll, so we can see exactly how we should proceed with like next week, and then maybe even week 8. We'll see if that's same response then. All right, waiting on a couple people. I'll give you all, let's think, 20 seconds to fill this out, or I will move on. No pressure. Ooh, okay, cool. I'm gonna end the poll here. So it seems like most people want to have a recording, and so I think we'll end up going with that. I got one suggestion saying that we could have a recording, maybe have an open time slot for like 30 minutes to an hour for people who need to ask questions. I didn't think that's a great idea, and so I think what we'll probably have is a recording for next week, and then check the Discord for the exact time, and we'll probably say when we'll be open for like a quick office hours, like a 30-minute office hours, to see if anyone has any questions about the recording. Is that cool with everyone? Awesome. All right, thanks for that feedback. Yeah, I realized that Mondays probably weren't the best day to choose for a track this quarter, but me being not the most, I guess, forward-looking person did not take that into account. So we'll deal with it now. But thanks for being pretty adaptable in these times. All right, so moving on, expected prior knowledge. And so hopefully you all are comfortable with coding, either through CS classes at UCLA or just on your own. Have some basic machine learning knowledge, either from beginner track or from your own experiences. And have some basic knowledge working with data like NumPy arrays or maybe pandas, data frames, things like that. So just general working with data in a programming language. If not, don't worry too much about it, but it might be a little bit hard to keep up at times, but there's always a beginner pack as well if you want to start from the basics, but hopefully everyone has this type of foundation or something close to it. All right, and so for today, we'll be going into, as I said before, regression, looking at logistic regression again, just reviewing it to make it's a really important part, and like I said, building block for neural networks in general. And then we'll be going and talking a bit more about machine learning in general, as well as some core concepts that are really important for machine learning and neural networks. And then finally, we'll be going into a bit about neural networks and starting to break it down into small pieces. Any questions about anything I've said so far? Logistics related, content related, expectations, things like that. Awesome. Just remember, if you ever have any questions, so feel free to interrupt or ask in chat and we will answer them. All right.
All right, so I'll be taking over and we're going to review linear and logistic regression, mainly because those were the main types of machine learning models or techniques that we learned in beginner track. So we will be building upon those and refreshing your knowledge of machine learning and both linear and logistic regression. So we have traditional programming, which has data and a program, and we write some algorithmic code and we get an output. But machine learning, however, kind of like generates a program based on our data and output. And so a great example of this and why we use machine learning is, for example, you want to play rock, paper, scissors with the computer. But to write an algorithm that does that, you would have to take into consideration how large your hands were and what color and all that. And instead of writing a traditional program, you could rather write a machine learning approach to it that would solve this issue. And this isn't my own example. It was taken from a TensorFlow developer. So this is a good example to kind of like wrap up this refresher. And the main core crux of machine learning is to use data to teach computers how to answer our questions and make it do what you want efficiently, like in the example. All right, so there are three types of learning that are major in machine learning. And the first one would be supervised learning. So supervised learning is that you have labeled data. So let's say we have a bunch of fruits and in your data, you have labels. Oh, okay, so the apple would be labeled as apple with the string or so on and so forth. And you have direct feedback and you have predicted outcome or future. So you send some input in and you have a predicted outcome based on labels and features that you were given. So you have unsupervised learning, which is another form of learning in machine learning, and you have no labels. So let's take the same fruits example without any strings. So no strings labeling each of the fruits. And let's say we have apples and watermelons. So the computers would have to, or the computer would have to identify which objects were similar to each other and which were not. So like you would have two clusters, two different groups. One example of this is k-mean clustering. And this is kind of finding a pattern, a hidden pattern in objects without any labeling. So when we go to reinforcement learning, we have a situation or an environment where an agent has to learn a policy and is evaluated based on a reward system. So you would have a decision process and you would be rewarded based on which set of moves gives you the best outcome. So for example, you're playing chess with a computer and the machine learning or the reinforcement learning here would be the best set of moves so that the computer would then win against you or another player. And this is based on reward to find the best policy, which gives you the winning move. So that would be your reward. So you could go. So the key elements of machine learning are the representation. So maybe like the model. So listed here. So e.g., we have a decision tree here. And you could have neural networks, which we will learn about later. So we're trying to find a model that best fits our data. So we're learning some sort of function or some sort of hypothesis that we will review in linear regression, logistic regression, or a model that best predicts our outcome. So that's our key element. So another key element of machine learning would be evaluation. So we would evaluate candidate programs or our hypotheses based on our cost, margin, entropy, or squared error. These are all types of per se cost functions or forms of evaluation. And we could also do things like evaluation metrics. The popular one listed here would be precision or recall, and a popular metric that uses both of these is called the F1 score. I don't know if this was covered, but it's popular metric, and these as well are popular. So that's one way to evaluate. And some other key elements of machine learning would be optimization. So candidate programs are generated. For example, trying to minimize the loss function over time. And this could be many features and many training examples, and you might be lowering your loss. So as you can see, this is a regression kind of model, and we're best fitting our data over time. And this is kind of like the gradient descent algorithm that we talked about before in beginner track. All right, so there are two types of modeling or classification tasks that we learned about. So that would be classification versus regression. So two different types of problems that we looked at, rather than saying classification task, because that's one of these. But we had either classifying a digit. This is from MNIST, so handwritten digits, and we have a neural network or a logistic regression model, as we saw before in our beginner track, trying to classify some set of digits or some set of data to find out the best outcome. So for example, we feed this into our neural network. We have a lot of handwritten digits, and for the probability for the handwritten digit 9, you get the highest, which would be 0.94. So we picked that one out. So we will be looking into MNIST and other image data as we go on into this track. So the other type would be regression. So you have predicting house prices. So we pass in maybe like an instance with a lot of features. So maybe like the number of bedrooms, the area, so like maybe the GPS coordinates and whatnot, and the year of the home, and we pass it into our linear regression model, which then generates a function based on learning from the training data, and it predicts 198,000 for 4,000 square feet, for example. So that would be regression. So what exactly is linear regression? So linear regression is a model that finds the equation of a line which best fits our data. So it could not only be like two-dimensional, it could have many features. So like I said, from the home prices, that I think that's an example that will later be illustrating in the slides, but a good one is home prices. So we have many features, and we want to generate a function that best fits our data. So the model learns from the training, and we pass in an input, and it gives you the predicted outcome. So predict outputs from given inputs. And notice the outputs are continuous. So this is a characteristic trait that will be very important in linear regression. So the outputs are continuous, as opposed to classification, where our outputs are discrete. So if we have only one number, so like we looked at handwritten digits, that number would be a 9. So there wouldn't be another number. And maybe if the model predicted wrong, it would be like a 2 instead of a 9, but it's only one outcome. Whereas this can have like a continuous set of outputs. So I don't know why this question's here, but this should be a regression because it says what is linear regression. Maybe that was part of the quiz before. So we have a hypothesis function. So we want to generate a function based on learning from our training data. So we have a single feature, for example. So let's just say that we're trying to figure out the price of a home just based on square feet. So we have hypothesis h of x equals b plus w1x. So usually we use our weights to like weight different features based on their importance. But let's just go for b plus w1x, and let's just say x is our first feature, and that's just the year of the home, or sorry, the square feet of the home, referring to the example that I first said. But you obviously know maybe this home, like this large rundown home, is as big as this mansion, but you obviously know that you don't want to buy this large rundown home. You'd rather buy a mansion, and that would probably be a higher cost because there's more demand for it. So there rises a need for multiple features. So we have a hypothesis function which takes in many features. So x1 to xn. So we still have that bias plus w1 x1 plus w2 x2 plus so on. So maybe you recognize this because it's similar to mx plus b. So based on our algebra classes before, but we weight all these features to then generate a function based on which features the model thinks is most deterministic of the home price if it predicts right. And that's hypothesis function. And another useful thing that I forgot to mention in linear regression is that the function would be linear. So linear regression, hence the name. So we have cost or loss function. So based on this cost or loss function, we're trying to choose the best hypothesis function from a space of hypotheses to find the best hypothesis that predicts our home prices or like whatever your problem is. So we have y hat or y cap is the prediction. So you have a caret symbol denoting your prediction, and y is the ground truth. So our first data set, like what's in the data set or why we already know, and m is the number of samples. So let's just say maybe this is like the training data. So m would be the number of instances in your training data, and y would be, let's say, okay, so we have this formula. So y hat I minus yi. So we know that the caret, the one with the caret, is our prediction from our model as we're training the model, and yi would be our ground truth or the y from the instance, and we would keep on doing this RMSE, so mean squared error, sorry, MSE, and we would try to reduce our loss function as we train further and further on. And this would be, yeah, so one way of trying to minimize the loss over time would be gradient descent. So we have to find a good learning rate. It's not mentioned, but a good learning rate, and we can use this formula because so where this partial derivative comes in is, for example, we saw the curve from before. So as you go on, you go down in a certain direction, and we adjust the weights based on the features deterministic ability for the actual output. So we want to find out the impact of a particular weight on the overall error. So for each feature, that's why we have like this partial derivative with respect to a particular weight. And over time, we adjust the weights to finally generate the best model such that each feature is pretty deterministic or like not deterministic based on what it is. So let's say over time, our model figures out that windows are the least weighted feature because they don't really matter for our home price, but maybe the year or the square feet of the home matters more. And this is the process that we use, which is gradient descent, to improve our model by training. So gradient descent continued. So we have, let's say, many dimensions for features. And over time, based on our WJ, J being the instance, so maybe 0 to how many features we have, and we learn based on that over time. So hence our partial derivative goes into this direction if you've taken multivariable calculus. Otherwise, just know that over time, our loss function is minimized over time based on minimizing the loss over time and making the accuracy better based on that. So another way to think about it is many iterations make the cost function converge to a local minima in more technical formal terms. Yep. So here's a review, and maybe you can post these in the chat. So let's start off with number 1. Which of these best describes machine learning during training? So you could post your answers in the chat just for a review. All right, I'll give you like maybe a minute. Okay. All right, so looks like we got a few answers. So most of the chat, an overwhelming majority, 100 out of 100, got B, data plus output is the program. So like we said before, we pass in the data and we pass in the output to judge the data based on our already ground truth, and we get a program based on it. And yeah, that's the correct answer. So number 2, the output of linear regression is what? So this is kind of a tricky question, but it was in the slides. So I'll give you some time to do that, maybe a couple of minutes. All right. All right, way to go. More people are answering than the first one, so that's good. Okay, so, well, I don't know because I didn't create these questions, but yeah, the answer is B again. Hence the question, did y'all actually randomize the answer choices? I have no clue. The output of linear regression is continuous, like we mentioned. So it could be a set of possibilities. Number 3, gradient descent does what to the cost function, considering that we wrote the gradient descent algorithm right. Yeah, so I'll give you some time to do it. One person answered, but do you all think that it might be the same answer? Okay, I'll give you a minute. Okay. All right. Yeah. So yeah, it happens to be B again. All right. So I know that that's such a great coincidence, but if gradient descent is done right, it should minimize the cost function. So yeah, that's the right answer. And yeah, so we're lowering our cost function. So minimizing. Yeah. All right. So classification models. So we talked about the regression models, so which were continuous, but classification models are primarily or basically discrete, and we only have one output. So some example problem spaces would be basketball recognition. So basically, so maybe you've all probably seen games from the NBA and people dribbling balls and shooting basketballs, and it's very huge in the industry right now because a lot of people are doing sports recognition models where they're looking at the balls or basketballs that are being dribbled or thrown around to better simulate video games or better predict where the ball is going to be at a certain point in the game using RNNs and other things. So another plausible classification model would be the one for MNIST. So you could say digit classification, so 10 classes. So you have 0 to 9 handwritten digits, as we saw from the MNIST data set. And we can pass in all these images to better classify from 0 to 9, one digit. And that would be our classification model because it's discrete. You can only have one number as your output. So another one would be object classification. So multiple classes. So maybe we'll see this towards when we go to our CNN models or when we go to do our project where we'll have many objects. So we'll have a cat, we'll have a plane, we'll have a ship and whatnot. And we're gonna classify these objects into multiple classes. So maybe you'll have different types of cats and that would be considered as a cat. And maybe you'll have different types of planes like a jet or a commercial airplane, and that would take a class as aircraft. So these are all classification models. And one type of classification model is logistic regression. So you can see, I don't know what example this would be, but let's consider an example that we didn't say before. So we would probably have, let's say this would be a destructive tumor, and this one would be a cancer tumor that's not that destructive or not that harmful. So the goal is to find the equation of a line or a decision boundary that best separates our data from different classes. So in this example, per se, we're finding a line that separates the orange region from the blue region, and that's our decision boundary. So that's an example of logistic regression for you. And it outputs values between 0 and 1, and or a vector that represents a probability distribution. So this is a multi-class. So let's go over both. So binary and a multi-class. So binary would be either blue or orange. So let's consider blue as 0 and orange as 1. So 0 or 1. And a vector that represents a probability distribution, a multi-class one, would be, for example, we looked at the handwritten digit 9, and it had 0.94 probability, whereas the other predicted outcomes probably had a small probability. So it would be like 0.01 for 1, 0.02 for 2, so on to maybe 0.94 for 9 if we had the classes as 1 through 9. So that would be our probability distribution or multi-class. So that'd be the vector. So we have logistic regression again. This is more in depth. So we have very similar to linear regression, except we're going to use a binary classification. So we have the sigmoid of Wx plus B. So what the sigmoid does is it gives you values from 0 to 1. So basically not 0 to 1, 0 or 1, two discrete outcomes, so 0 or 1. And this is for binary classification. So like maybe blue is 0, orange is 1. And when you pass it into the sigmoid, because our logistic model is very good, we would get 0 if it's anywhere in the blue region and 1 if it's anywhere in the orange region. For multi-class classification, we have a softmax function. I was told that this might not have been covered in the beginner track, but we'll just kind of run through this. So what a softmax function does is it does multi-class classification to produce a probability distribution. So this would be like this 3-dimensional image going down. And we would try to classify multiple classes, and we would have a probability distribution. And the one that would have the highest probability of occurrence would be our predicted outcome, our final predicted outcome. And to kind of visualize both of these, the first one would be our sigmoid function, and the second one would be our softmax function. So yeah, that's logistic regression. Yeah, so we'll take a look at something else, which is, okay, so handing it off to our other officer to cover. Yeah.
All right, perfect. So as you guys probably noticed, one aspect of logistic regression that really differentiated from linear regression was the fact that logistic regression had an activation function. And so essentially what the activation function's main purpose is just to take the output space of the linear regression and you just kind of like compress it into a more manageable space like 0 to 1. And so what the logistic regression function will do is that it will give us an output of anywhere between 0 to 1. And then based on our decision boundary, that's how we kind of determine exactly which class the data will fall into. And so depending on the type of like model that you're trying to deal with, you're going to have like different activation functions as Pritham described earlier. And we'll go more in depth on how you kind of like distinguish like which activation function to use and like when. All right, and so were there any questions for this, I guess, like review part of linear or logistic regression? All right, perfect. So if there aren't any questions, we'll just have like a quick little review session. So for question 1, which of these describes a regression problem? And if you just want to like input your answers in the chat. Oh yeah, okay. So Jeffrey said that they didn't cover softmax last quarter. So if there are any resources that you guys could look at, if you would like, we can probably compile some resources for you to look at. I'm pretty sure the beginner slides also has something about softmax too. So like we can probably send that over. Yeah, and we'll also be covering softmax a little more into the quarter as well. All right, so back to the review. Does anybody have any kind of like guesses on like which one of these would describe a regression problem? Okay, so based on your guys' answers, you guys said that you guys chose A, which is predicting the amount of rainfall in inches based on the temperature. So you guys are so that is like one type of a regression problem. So that would be linear regression. Yeah, I guess this question could have definitely been worded a little bit better. Yeah, so kind of like either one would have worked because B would represent logistic regression, which is kind of, yeah. So it's like a little bit different, but they're both like regression problems. Okay, so number 2, what is the output of logistic regression that is binary is? So which one of these 4 answers? Okay, we'll just give you guys like another like 20 seconds. Okay, all right, so let's see. All right, so you guys chose D, which is definitely an acceptable answer because logistic regression, the output is definitely going to be between like 0 to 1 if we use like the sigmoid function. Yeah, and then exactly, Jeffrey. Yeah, so, or let me see. Oh, actually, kind of, but not really. So even though we do technically have like continuous values from like 0 to 1, the actual output of logistic regression, when we have that decision boundary, is going to separate the data into different classes, or at least in this case, 2 distinct classes. And so because we have like these distinct classes, that's why we kind of consider it discrete rather than just only numbers between 0 and 1. Okay, cool. All right, so now that we have finished reviewing everything, we're going to dive right into neural networks. And I'm sure like you guys have probably heard neural networks before because it is one of those, like machine learning buzzwords. So I guess like today's objective was just to give you guys like an introduction to neural networks, their functionality, the components, and like why we even care about them. So let's get into it. Alrighty, so here we have a diagram of just like a classic vanilla neural network. And just so you guys know, the white circles that are in the blue boxes, those are going to be our neurons or our nodes. And then the white circles in the red boxes, those are going to be the input data or features, as you can see, because this is like the input layer. And then so if you notice like the arrows that are connecting the neurons together, they're just kind of the way that these like nodes or neurons are able to communicate with each other and like pass information throughout the network. And essentially what this diagram is just supposed to show you guys is that neural networks can be made out of multiple layers. So you have like your input layer and this one has 2 hidden layers and then an output layer. And then within each layer, you can have multiple neurons within it. And then they all make all these connections, which is kind of why we call it a neural network. And essentially, it kind of like roughly imitates sort of like the design of like our own human brain. And the goal of like a neural network is just essentially to help the computer kind of like mimic the cognitive abilities of our own brains by giving the computers like the ability to learn as well as like distinguish patterns. And yeah, so that's pretty much like what this diagram is showing us. And then so if we go into more of like the nuanced components of a neural network, we'll have our artificial neuron. And so what exactly is an artificial neuron? Well, essentially at like the very basis, an artificial neuron is just simply a mathematical like formula. And so what we use here is very similar to the logistic regression equation. And so each artificial neuron, which is like the green thing over here, and yeah, the green thing. And then so we will have a weight, which kind of like tells us how important like the neurons are in terms of like the output. So if we go to our example on the right corner, as you can see that this example is trying to identify like what type of fruit. So let's say that maybe we're trying to figure out if this is an orange. And so if you see on like the neurons on the red neurons or like the features, you have like the color or like the shape. And so let's say that like depending on like what you're trying to look for, here we're trying to find an orange, we'll probably say that like the color of an orange is probably like one of the most distinguishable features. And so because that feature is like more important or has higher priority, we would have that neuron have like carry a heavier weight rather than like the shape. So that's kind of like what these like weight vectors are for. And then on top of that, we also have our activation function, which essentially just kind of like tells us, which helps activate like neurons based on like a certain threshold if they are able to like cross it. So that's essentially like what an artificial neuron is. And then now let's look into what happens when we start like connecting these neurons together. So yeah. So when we start connecting these neurons together, we start creating different types of models. And so at the very basic level, probably like the most simple model that we have is a perceptron. And so a perceptron and logistic regression are pretty much the same thing. However, they do have some subtle differences, but just for the sake of this workshop, we'll consider them to be the same. And so as you can see, the perceptron has like an input layer with its own like nodes, with their own like weights, biases, and then it goes into like the output layer. It's relatively simple. And then with the single layer neural network, that is when things get like a little more complicated. So sometimes like these single layer neural networks or just neural networks in general can be called like multi-class perceptrons. Because if you see, it's essentially, you're just kind of taking perceptrons and you're just like stacking them on top of each other, kind of like Legos. And so essentially with this, you're able to kind of have a model that's a lot more sophisticated. It's able to create like a lot more like connections and recognize a lot more like different patterns with the data. So essentially what we have here in the single layer neural network, we usually call this one like a fully connected neural network or a dense neural network, because if you notice all of the neurons in like the layers after the input layer, they get information from every neuron in the subsequent, or yeah, in the previous layer. So that was a little bit confusing. So let me try to like break it down a little more. So if you notice the first purple neuron, it gets its information from all 4 of the neurons in the previous layer. And then the second purple neuron also gets all of its information from all 4 of the neurons in the previous layer, or the blue layer, as well, like the input layer. And then the last neuron in the hidden layer will also receive information from all 4 neurons. And so if you notice, that's how you kind of connect the layers in a neural network together. And one important thing to note is that neurons do not connect with other neurons within their own layers, but only within layers that are like right after it. Yeah, and so that is essentially kind of like the basic like architecture or diagram of a single layer neural network. Right, perfect. So this kind of leads us to like the big question of why do we even bother? Like, why do we even care about like neural networks and making like more complicated models instead of just using a simple logistic regression formula? Well, the great thing about neural networks is that it gives us a lot more representational power. So the cool thing when we use these neural networks is that we're not only able to kind of like analyze data that is linear, but we're also able to add non-linearity into our relationships, which is really big because in the world that we live in, a lot of events aren't necessarily linear. So to have a model that is able to kind of understand those relationships is definitely really helpful. So there's like a cool little demo on the slide if we want to go check it out. I think it's a very great visual. So if you look at the data that we have right now, as you can see, it's obviously not a linear, it's not a linear model. The data is not linear because you have all the blue dots like in the circle in the very center, and it's surrounded by like the orange dots. And so this model is just trying to classify like whether the dots are like blue or orange. So let's see what happens when we only have like a perceptron. So no hidden layers, and it's just the features and then straight into the output. Oh, no hidden layers, or yeah. Okay. So if you recall, a perceptron is just kind of like a basic logistic regression equation. And so when we put it through this program, you can kind of see that this model is not really able to kind of fully understand the different relationships that are found with the data, especially when it comes to like classifying this nonlinear relationship, because you can see that it kind of like divides the screen up into like orange or blue, but like not quite in the right way. And then so if we stop that and then we add like one hidden layer with like 3 neurons, okay, and then we run it. And as you can see, just by simply adding one hidden layer, we're able to already get a model that is a lot better at kind of like handling this type of data. And so it's able to make more nuanced connections as well as see these patterns that like a simple logistic regression model may not be able to see. So while this is not like perfect, it's definitely a lot better than like just using like a classic perceptron or just relying on simple like regression models and not like neural networks with like hidden layers and stuff. All right, so that's for the demo. The link's in the slideshow, so if you guys want to go check it out later on your own, you totally can. Okay, perfect. And then so just for like next workshop, we're going to dive more deeply into neural networks, get into like more of like the details. So next time we're going to be like defining the architecture of neural networks, understanding like forward propagation and like getting predictions, kind of like going into more detail on computing laws. Yeah, and then like the functions, the weights, and then we're also going to start learning how to perform gradient descent and how the model kind of like adjusts the weights and like the biases. And then we're also going to start covering back propagation, which is really important. Then, yeah, so there's going to be a little math involved. Okay, yeah, so any questions? Okay, all right. If not, Nikhil can take it away.
Awesome. Thanks, Angeline. All right, so as of now, there's no upcoming events for like other committees, so I'll skip this part. But for next week, we're talking more, as Angeline said, about neural networks, but mostly about backpropagation. And so backpropagation is really where we leave beginner prac a bit behind and move on to more neural network focused things. And so it's one of the most important concepts in deep learning that's used like an ambient neural network. And so really recommend turning into the recording. It's going to be a really fun and interesting concept to learn. And with that, I was going to say thanks everyone for coming. I know it's a bit short today, but it's also the first workshop, and we'll see just like a quick review as well as a bit of introductory content. As I said before, if you guys could all fill out the feedback form, that'd be great. We always appreciate your feedback and always take it into account for next week or in future weeks. And if you haven't joined the Discord or join a Facebook group, we recommend that too for any updates. And we'll be posting both the recording of this week and next week on the Discord. So please join that if you can. The link is at the front of the slides. But yeah, but if you have any questions, feel free to ask them. Otherwise, that's the end of the workshop. Thanks everyone for coming. Oh, I stopped the recording.